What if I told you that there's a hidden blueprint connecting your social media feed, the London Underground, and pretty much every movie ever made? It sounds kind of complex, right? But it's all built on one single, really powerful idea that explains how just about everything in our world is connected. So let's go explore it. Seriously, just think about that for a second. How many handshakes, how many introductions would it take to connect you to anyone else on the planet? I'm talking a pop star, a world leader, or even a villager in some remote corner of the globe. It feels like an impossible question, right? Well, believe it or not, it's a question scientists have actually tried to answer. In fact, way back in the 1960s, this exact question totally obsessed the psychologist Stanley Milgram. He wanted to take this big philosophical puzzle and turn it into a real-world experiment to solve what he called the small world problem. And the experiment he came up with? It was just brilliant in its simplicity. Okay, so here's the deal. He sent out packages to almost 300 random people in the middle of the country, Nebraska and Kansas. The goal? Get that package to one specific stockbroker living all the way over in Boston. And here was the one crucial rule. You could only send it to someone you actually knew on a first-name basis. So what do you think? How many steps did it take? 20? 100? The result was, well, it was stunning. For the packages that actually made it, the average number of steps to get clear across the country was only about 6. Just 6. And that single number is what gave birth to the famous phrase we all know today, 6 degrees of separation. That's such a fantastic story, but it kind of begs the question, right? What's the underlying structure here that makes our world so small? How can we actually map out and see these connections? Well, the answer is a simple but incredibly powerful tool called a graph. Now, when I say graph, I'm not talking about, a bar chart from a business meeting. No. In the world of computer science, a graph is just a way to model a network. And it's made of only 2 things. You've got vertices, those are the dots, which can be people or places or anything really. And then you have edges. Those are the lines that connect the dots and show the relationship between them. That's literally it, dots and lines. But here's the thing, not all connections are created equal. You can have an undirected graph, which is basically a two-way street. Think of a friendship on Facebook. If you're friends with someone, they have to be friends with you too. It's mutual. But then you've got a directed graph, which is more like a one-way street. A perfect example is Twitter or Instagram. You can follow a celebrity, but that definitely doesn't mean they're going to follow you back. The connection only goes one way. And you can really see the difference here. The undirected graph shows those mutual, two-way links, but the directed graph has arrows that show the relationship is flowing in just one direction. And believe it or not, this little distinction is absolutely crucial for understanding how different networks actually work. So where do we actually see these graphs out in the wild? Oh man, they are literally everywhere. This, for example, is the Hollywood Actor Network. Every single actor is a vertex, a dot, and an edge connects any 2 actors who've been in the same movie. And yep, this is the exact graph that powers the famous 6 degrees of Kevin Bacon game. Or how about this one? A map of the London Underground is a perfect real-world graph. I mean, think about it. Every station is a vertex, and every track that connects them is an edge. It's the hidden blueprint that helps millions of people find their way around a massive city every single day. But it's not all games and transportation. Graphs are also incredibly powerful tools for some really serious analysis. What you're looking at here is a network map related to the 9/11 attacks, based on research from Valdez Krebs. By turning individuals into vertices and their known connections into edges, intelligence agencies can use this kind of graph theory to uncover hidden structures, find key players, and really understand how information moves through complex social networks. Okay, so we know what a graph is, but if you're a computer, how do you actually explore one? How do you systematically walk through the whole network to make sure you visit every single dot and every single line? Well, that process is called graph traversal, and there are 2 main ways to do it. First, there's depth-first search, or DFS for short. I like to think of this one as the deep dive. You pick a path and you just go as far down that rabbit hole as you possibly can before you turn back. The other way is breadth-first search, or BFS. This is more like a ripple effect. You explore the network one layer at a time, visiting all your closest neighbors first. So let's see DFS in action. Say we start at dot A. Since we're doing the deep dive, we're going to go from A to B, then B to C, C to D, and all the way down to F. Uh-oh, dead end. So now we backtrack just enough to find the next path we haven't explored yet, and that takes us over to E. So the final order we visit everything in is A, B, C, D, F, and then finally But what about BSS? With our ripple effect strategy, we get a totally different result. We start at A again, but instead of diving deep, we go wide. We visit all of A's immediate neighbors first, which are B and C. Then, we move out to the next layer and visit their neighbors, D and E. And finally, we get to that last layer and visit F. The result is a much broader, layer-by-layer kind of exploration.
So traversal is about visiting everything. But what happens when the order you visit things in is absolutely critical? What if some tasks have to be done before others can even start? This is where graphs basically become the ultimate to-do list.
Think about it like signing up for classes in college. You can't just jump into advanced calculus your first semester if you haven't passed intro to algebra. One thing depends on the other. And that creates a very specific kind of problem that needs a very specific solution. When you try and map out all those dependencies, you might get something that looks, well, like this. It's a total jumbled mess of arrows, right? So the big question is, how do you take this chaos and turn it into a single, logical, step-by-step plan where you actually do everything in the right order? The answer is this beautifully elegant algorithm called topological sort. It's like magic. It takes that complex web of chaos and just flattens it into a straight linear path. As you can see, the mess gets transformed into a crystal clear plan. It guarantees that by the time you get to any task, everything you needed to do beforehand is already done. And now let's talk about maybe the most practical, everyday use for graph theory: finding the shortest path. And trust me, we all use this constantly, whether we know it or not. Every single time you pull up a Maps app on your phone and ask for directions, you're asking a graph algorithm a question. But what exactly are you asking? When you say, give me the shortest path, what does shortest actually mean? Does it mean the fewest miles, the fewest turns, or the fastest time, avoiding all the traffic? And this is the key idea we really have to get our heads around. In a complex network, the path that looks like a straight line, the one with the fewest stops or turns, is often not the actual shortest or best path to where you're going. And here's why. We can assign a weight or a cost to each edge in the graph. That weight could be distance, sure, but it could also represent travel time because of traffic. It could be the price of a plane ticket, or even how difficult a project task is. The goal of really powerful algorithms is to find the path with the lowest total weight. And that's what gives you the truly optimal route. So there you have it. From 6 degrees of separation, to mapping out your to-do list, to just navigating your daily commute, this simple blueprint of dots and lines is quietly structuring our entire world. It's the hidden language of connection. And that really just leaves us with one final question for you. Now that you can see the networks, what hidden connections are you going to start discovering in your own life?